Imagine witnessing a star explode in a cosmic spectacle so unusual that it hints at a rare dance with one of the universe's most mysterious objects, a black hole. This astonishing event, detected by the Zwicky Transient Facility, ZTF, in July 2023, challenges our understanding of how supernovae and black holes might interact. But here's where it gets controversial. Such interactions are thought to be incredibly rare. Yet this explosion, captured about 730 million light-years away, could be direct evidence of a star actually being engulfed by a black hole. The ZTF tirelessly scans the sky for transient phenomena, meaning objects that fluctuate or suddenly appear in brightness. This automated survey uses cutting-edge technology, and now, with the help of sophisticated artificial intelligence, it flags unusual signals and sends instant alerts to astronomers worldwide. The 2023 detection of this peculiar light signature, later named SN 2023-ZKD, triggered rapid follow-up observations from multiple telescopes. This quick response was vital because studying how the brightness changed over time is crucial for piecing together the underlying astrophysical puzzle. The detailed findings were published in the Astrophysical Journal under the title Evidence for an Instability-Induced Binary Merger in the Double-Peaked Helium-Rich Type IN Supernova 2023-ZKD. Alexander Gagliano, a fellow at the NSF Institute for Artificial Intelligence and Fundamental Interactions, led the research. The supernova's host galaxy, PS0J154847.59 plus 09100, lies roughly 815 million light-years from Earth. The researchers compiled data across ultraviolet to infrared wavelengths, revealing a strikingly unique profile. Archive images showed that the region had been quietly glowing for years before the supernova's official discovery, with a persistent and luminous output for nearly 4 years that ramped up gradually in its final year. After SN 2023-ZKD's outburst, astronomers observed 2 distinct brightness peaks, spaced about 240 days apart, an unusual pattern for such cosmic explosions. The photometric data captured from various observatories painted a compelling light curve. After first being spotted, the supernova's brightness climbed steadily for about 2 months, then brightened again after a seasonal observational gap caused by the sun's position. Following this, the brightness fell for close to 6 months before experiencing another dramatic surge. These complex fluctuations highlight that something atypical was unfolding. What's truly remarkable and rare is this gradual increase in brightness before the explosion. Normally, supernova erupt suddenly without such prolonged pre-explosion activity. To decode this odd behavior, the team explored several scenarios. They considered a single massive star undergoing core collapse, but this did not fully align with the evidence. SN 2023-ZKD showed traits resembling either a luminous blue variable, a type of massive star known for erratic brightness, or a carbon-rich Wolf-Rayet star, which also ends its life violently as a supernova. Yet neither model fit perfectly. Another hypothesis of a hydrogen-rich Wolf-Rayet star shifting into a luminous blue variable phase was also ruled out. Instead, the team proposed a bold and fascinating explanation. SN 2023-ZKD was the result of a binary-driven merger supernova. In simpler terms, the exploding star was in a close binary system with a massive companion, the black hole. Before the explosion, the star was shedding layers of material into the space around it. The first brightness peak likely occurred when the supernova shockwave collided with this ejected material, while the second peak emerged from a slower, more prolonged interaction with a dense, disc-shaped cloud surrounding the system. This unstable environment hinted at the intense gravitational tug-of-war between the star and its black hole partner. Lead author Gagliano explained in a press release that this event provides the strongest evidence so far that a black hole's close encounter can directly cause a star to explode. He emphasized how AI was crucial. Their machine learning system had identified SN 2023-ZKD months before its unusual behavior intensified, giving astronomers precious time to gather extensive observations. The researchers also explored an alternative idea, that the black hole might have completely torn the star apart before it exploded, and the supernova-like light was generated as the stellar debris spiraled into the black hole's accretion disk. Regardless, their analyses confirm that a black hole remained after the event. Co-author V. Ashley Villar pointed out how SN 2023 ZKD shows some of the clearest signs yet of a massive star interacting with its companion in the years just before a supernova. This discovery could unveil a whole hidden class of explosions that AI will help bring to light, reshaping how we understand late-stage stellar evolution. The team's model, illustrating how the star and black hole binary evolved, is fascinating. Between 1 and 5 years before discovery, the system experienced 2 intense outbursts that ejected about 2 times the mass of the Sun each. These caused the initial variability seen in the light. Then, during the final pre-explosion year, runaway accretion, a process where mass rapidly transfers from one object to another, tightened the binary orbit, resulting in a steady brightness increase caused by either enhanced accretion onto the black hole or a burst from the star itself. The first major brightness peak marked the moment the star merged with the black hole and exploded. Following this, the collision of ejecta with the first helium-rich shell created the initial peak, while interactions with a second shell were responsible for the later brightening before the supernova eventually faded away. From their data, the authors deduced that the merger involved a star roughly 30 times the mass of our Sun and a black hole about 10 solar masses. This cataclysm followed years of unstable mass transfer between the two objects, but many details about the exact mechanisms remain to be clarified. The team recommends continued multi-wavelength monitoring of SN 2023 ZKD to better understand the properties of the circumstellar material, the gas and dust around the star, and to confirm both the theory of core collapse explosion and the binary interaction origin. Looking forward, the arrival of the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, in 2025 promises to revolutionize supernova discovery, potentially uncovering around 100,000 such events yearly. As Gagliano reflected, this breakthrough underscores the critical importance of studying how massive stars and their companions interact as they near the end of their lifetimes. Although we've known that many massive stars exist in binary pairs, witnessing one exchanging mass just before exploding is exceptionally rare and invaluable for astrophysics. What's exciting is that future surveys like the Vera Rubin Observatory and Pan-STARRS will not only spot these spectacular events, but will also leverage AI to detect and categorize them among the astronomical data deluge in real time. This technological synergy means we're entering an era where catching these fleeting cosmic dramas as they unfold, rather than after the fact, will become routine. Algorithms designed to detect long-lasting and re-brightening transients will play a pivotal role, helping scientists capture the full variety of exotic stellar explosions. So, what questions does this